The lectures are online here, and they're also online in the Collège, the site of the Collège de France, and I guess there's supposed to be a video as well. However, I think that the slides are at a different site from the supplementary notes, which I'll try and fix. So the first place to go to is the one in blue. That would be the best thing to do. I also have an address here. I have an address in the Collège de France as well, but the password doesn't work. So, okay. So this is the first of two lectures on the theme of, well, we'll see that it's a rather broad theme, but starting with single qubits and going on to what I call spin nets. And you'll see that this is a rather broad theme. And in fact, I'm going to spend the first 15 minutes of the talk discussing what all this means in a rather informal way. So you'll see that there's a very wide selection of themes that we can discuss, and I will focus on certain of them. So, one way to imagine this is to imagine an alien race voyaging through the galaxy and coming across the Earth and asking what is significant about the Earth. And if you're a biologist, you would be appreciating more and more that what's significant about the Earth is not, in fact, the existence of humans, but the existence of a very large set of interacting networks of information. And so I'll discuss this a little bit. The first thing you notice when you're looking for networks in nature is, of course, regular structures. And I'm going to be discussing some of these in the context of real experiments. So one notices, of course, regular crystal lattices. Sorry, I keep on mixing these up. I'm on the wrong slide. Regular crystal lattices. They may have a rather complicated surface structure, and the problem, the field of surface physics is concerned with this. Surfaces are very important because they're the site of catalysis. Catalysis is one of the fundamental reasons why life exists on Earth, particularly autocatalysis. We would also notice random networks, and we might imagine that they contain no interesting information, but this is actually not true. And there's a very nice review for those of you who have mathematical interests on this topic, which analyzes the structure of disordered systems according to what is called ultrametric geometry, or ultrametric sets. So when you analyze the structure of these according to this idea, you find that there's a hierarchical structure inside these systems, which is extremely interesting. So in other words, order can be obvious, spatial order, or it can be hidden, as in the case of, for example, one-dimensional spin systems or disordered solids. And I mentioned before that the most obviously interesting thing about the Earth from the point of view of an alien intelligence would be the existence of all of these interacting networks. So you notice them all over the place. This here is, oops, I keep on hitting the wrong one. This here is what's called a disease network. It's a network of information in which the nodes here are different diseases. And the interactions are mediated by so-called gene-protein networks, which play a fundamental role in all living things, and which are, if you like, governed by almost an extreme Lamarckian inheritance pattern. That is to say, they don't inherit things, they acquire them. So it's exactly the opposite of what we're told in school about genetic inheritance. In fact, stem cells are the unique kind of cell which does reproduce the genetic information in it. All the others acquire characteristics, and this is very important. So this is a network which is of great interest to me right now, since I just got back from the US. It's the network concerned with, it's the so-called circadian network. It makes sure that you wake up at the right time and go to sleep at the right time. And it's quite extraordinary because it involves interactions between everything from the sun and moon and our sensory perception of them to, in fact, rewriting or, if you like, reprogramming of genetic networks with proteins. All of this is operating together. So this sort of thing actually reveals something that's very important in all of these networks, which is that there's actually a duality in these networks between the nodes and the links. And this is something that physicists are very used to. We are accustomed to taking some network with nodes and links between them, and then transforming it into another network in which basically the links become the nodes and vice versa. And actually this is something that is becoming more and more popular in biology. This is an autocatalytic network. It's a network in which you start off in chemistry with a number of species which interact. In this case, they're called A and B. And they produce compounds, but they also produce more of A and B. And this means that the product, some of the products of the reaction are compounds, which are different from A and B, but also some of the products are actually the original reactants, A and B. What that means is if the A and B, or one of them, can catalyze this interaction, by which we mean lower the energy barrier to make it go, it means that the reaction is catalyzing itself. And and you can form more and more complicated networks of this kind. And of course, networks like this kind have an enormous advantage. They compete with other kinds of reaction chain, and they win because they're catalyzing themselves. And in fact, that's now understood to be the basis of the formation of not just life, but all sorts of complicated networks on the Earth and elsewhere. For example, on interstellar grains, which is where many complicated organic molecules are synthesized. So, moving on now to the interests of physicists, for a long time it was a thought that in biology that all processes involving what biologists like to call functional processes in biology were classical. They were basically what Bennett once called Brownian computers. That is, they move really slowly through a diffusion process. The processes depend, in fact, on temperature and classical activation. But in the last 8 years, more and more evidence has been accumulating that this is actually not the full story. I'm just going to mention two such phenomena here. One is the phenomenon of navigation. So it's well known that migratory birds navigate using the Earth's magnetic field, amongst other things. It's one of the things they use. For a long time, it was assumed that this was a classical mechanism, that they were magnetic particles, probably in the beak, which they used to sense the direction of the Earth's magnetic field. But there's now very good evidence that that's actually not the case, that the main mechanism is one involving Einstein-Podolsky-Rosen pairs of free radical spins. So a photon comes in and generates, it basically excites an electron from what a solid-state physicist would call the valence band into the conduction band. In a molecule, basically it creates a free radical which is mobile. Solid-state physicists would call this a dangling bond or a free spin. So we have two spins. One of them is moving around the molecule, and the other one usually stays in the same place. They remain entangled because there are only two things that can disturb this. One is the interaction with phonons, but the spin-orbit coupling is very weak in these systems. And the other is the interaction with nuclear spins. So this Hamiltonian here involves the interaction between the Earth's magnetic field and these free radical spins. K sums from 1 to 2, as well as the interaction between these spins, the free radical spins, and the nuclear spins. Well, the molecules are oriented in the eye. So they all point in the same direction, which means that the hyperfine fields are also oriented, which means that the dynamics of this pair of spins depends entirely on the relationship between B, the Earth's field, and these hyperfine couplings. And so the spin dynamics of this pair of spins depends on the relative orientation of the Earth's magnetic field and the hyperfine field, and they're basically of the same strength in these molecules. And it's actually quite complicated, so I'm not going to go into it, but remarkable experiments have, for example, applied AC fields which resonate with the hyperfine fields and at very low intensity, 1/10 of a nanotesla, so far less than the Earth's field. But if they're tuned to the hyperfine frequency, the birds can't navigate. It's quite remarkable. Another example of such a process is the harvesting of energy from the sun by plants, so-called photosynthesis. We now have remarkable experiments done in Berkeley, Toronto, Princeton, and Chicago, which show that the key process in harvesting of light involves, so the molecules involved, this is a typical molecule. It has a molecular weight of 10 million. It's enormous. It's made up of 48 so-called chromophores, which are large submolecules, each of which contains some chlorophyll. The chlorophyll is basically like a two-level system. It's like a single atom two-level system which can absorb light at a specific frequency. And for a long time it was assumed that all of the chromophores in this molecule are absorbing the light independently, and that the energy was moving around in the molecules between these chromophores by a diffusive process. This is, if you like, the dogma of biology that everything has to be classical. We now know that, in fact, these molecules are like giant antennas. The photon is absorbed in a superposition of, it's completely delocalized over 48, in this case, different two-level systems. And in fact, the energy is, so if you like, the wave function of the excited state is being shared coherently between all of the different chromophores. There's a thing called a reaction site in this molecule which eventually absorbs the energy. And the dynamics is set up, it seems, so that the decoherence time is roughly equal to the time it takes for the energy to be taken up by the reaction center. Now this is over a length scale of roughly 100 angstroms. It's quite a large superposition of states. Now you see that the kind of Hamiltonian that one is using here is one that's very familiar to people both in quantum optics and in solid-state physics and elsewhere. We have hopping between sites, possibly with a gauge potential here, and we have an energy on the different sites. And CJ cross creates, in this case, an exciton on one of these sites, and the exciton can move around between them. Now, I have no coupling yet to an environment, but that's the kind of model that we'll be talking about. It's a network in which the object of interest is carrying information. Qubits. So this is where we attempt to do this sort of thing artificially. I should, by the way, point out that one of the remarkable things about these is that their quantum efficiency exceeds 99%. It's quite incredible. People in the energy industry would love to have such a system. Now, in nature we find, well, of course, lasers and masers at very large scales. This is, oops, keep on hitting the wrong one. This is a quasar, and there's a maser in this whose power emission is something like 10 to the 9 suns. It's very large. Astrophysical masers have been known for a very long time. But people have been interesting themselves in in making qubit networks in many different ways. This is an ion spin chain with tunable interactions between the spins. This is a solid state. One of the systems that's of interest to solid state physicists, as I'll discuss. This is an almost perfect quantum Ising system with tunable interactions. More attention so far has been focused on superconducting networks of qubits and also networks of spins in semiconductors, both of which, well, the spins in semiconductors have attained extraordinary coherence times now of order half an hour. It's quite extraordinary. The main experiments are being done at the moment in Australia. Superconducting networks are used in these quantum annealing systems, which is sometimes called adiabatic quantum computation, principally by the company D-Wave in Vancouver, and they now have a network of 4,096 superconducting qubits. So this is already out of date. And of course, this is the vision that people are thinking of for quantum computation in the long-term future. And all of these are, of course, networks of quantum mechanical two-level systems operating in the quantum mechanical regime. So it's actually interesting that you can make all sorts of mappings between sets of qubits, interacting qubits, written in the usual gate formulation. So as a set of interacting logical gates, and the kind of quantum walks that I've been talking about. In other words, the motion of some object between nodes using various links. So it is possible to explicitly map all of these things to each other. So this is a set of gates. This is a representation of 3 interacting qubits, actually. So we have 8 possible states for 3 qubits. And they're represented here in the notation that's used in quantum optics, and here in a different notation, but they're basically the same. This is another way of representing them. And this is a way in which you simply refer to each point here as a node, and these lines here are the different couplings between them. And as I say, you can map any of these representations to this, and vice versa. Actually, these are more general than this. And of course, the Hamiltonian of one of these networks is simply what we've already been looking at. We have hopping between the different nodes and energies at each site. And crucially, in a quantum computer, these things can be varied in time. That is to say, the local energies on each node or each site can be varied as a function of time. So for example, in a nuclear spin quantum computer, one applies successions of pulses to change the interactions in this formulation. But changing the interactions, it simply means changing the hopping matrix elements or the on-site energies in the nodal representation. So in fact, what one likes to do in quantum information theory is study the propagation of a particle on some kind of a graph. And if you have more than one quantum computer, you could have more than one graph, and they would be interacting with each other. And one can study the dynamics where you ask yourself, how does things depend on the time dependence? How do they depend on the connectivity? And so on and so on. Now, of course, this way of formulating it is much more useful to a theoretical physicist. And we'll see that we learn a great deal about quantum computation by studying the motion of particles. So this then becomes a problem once I've added an environment of quantum relaxation on some graph in which the parameters can be changed with time if we want. If the parameters are all independent of time, then what we're dealing with is a quantum memory. Now, I've said nothing yet about decoherence, and as most of you will know, the biggest problem in building a quantum computer is decoherence. So that is indeed going to be one of the main topics of the discussion, but so far I've said nothing about it. If you want to see all of the explicit mappings, they're in this paper. Okay, now, before we start talking about a network, we have to start talking about the dynamics of a single qubit, which seems at first to be very simple. We're talking about a two-level system. It's hard to get simpler in quantum mechanics. But of course, we're going to be coupling it to our background environment, so we want to see what happens. So in the following, I'm going to discuss, first of all, some of the basic theoretical results, which have mostly been known for a while. And of course, people whose background is quantum optics will immediately think in terms of the interaction of of an atom with a photon, discussed in great detail, for example, in the book of Cohen's energy, and in fact in many elementary quantum mechanics books as well, at a lower level. But a key difference here is that the coupling that one assumes in quantum electrodynamics is rather special, and we want to be a little bit more general than that. Okay, so this is the second part of the lecture, and it'll be more theoretical. And the third part will, as I've done before, discuss an example, a real-world example. Okay, so when we look at a single qubit, of course, we start off with a very simple Hamiltonian, which is here. And I'm going to write the Hamiltonian of the qubit in this form quite often. So I'll have what you can think of as a transverse field term here along the x direction and a longitudinal field here. So in other words, the field is in general pointing in some direction in the xz plane. Now, one can easily calculate the time dynamics of this with some arbitrary initial state. We will normally not be calculating the dynamics of the wave function of this, but rather of the density matrix. So let's just notice how simple this is. If we, in a phenomenological treatment, or in an approximate treatment of the dynamics of this qubit, one assumes that the time evolution of the density matrix for the spin will have the following form. So if you like, you can divide by 2 on both sides. So we'll have diagonal elements, which in the absence of any coupling to a bath, will just look like 1/2 of 1 plus cos delta t on the diagonal, 1 plus or minus. And on the off-diagonal elements, we'll have I sine 2 delta t. So of course, this is simply, so let me make sure you understand. This is the matrix element up, up. This is down, down. This is up, down, and this is down, up. Okay, so these are the time evolution. This is the time evolution of the 4 different matrix elements of the 2-level of the qubit density matrix. And then phenomenologically, we add, when we discuss the coupling to a bath, we add these relaxations here. So this is actually what's called longitudinal relaxation, or it's called a T1 process, or it's just called energy relaxation, the various names that it's given. The off-diagonal relaxation here, gamma 2, behaves differently in general in time, and this is usually called phase relaxation, or decoherence, or just T2 processes. And in fact, if we assume that these functions of time here, gamma 1 and gamma 2, are just constants times time, in other words, if we have purely exponential relaxation, then there are definite time scales, T1 and T2, associated with this. And in that simple picture, we would have the off-diagonal matrix element decaying in this way. This is precise. I'm simply plotting the imaginary part of this function here. And the Fourier transform would just be a standard line shape that we expect. So I'm assuming that this is all completely obvious to you because it's what you learn at the very beginning in quantum optics. The problem is that it's actually not true except for certain kinds of system. What you require in order for this simple picture to be true is that either the bath couples weakly to the qubit, or that there are no memory or feedback effects from the bath. In other words, that the bath doesn't react back on the system as time goes on. And I'm going to discuss for you when these conditions are valid. They obviously are valid in quantum optics most of the time. Now, this sort of result is derived in many fields using either some kind of quantum master equation or something simpler based on that. But we're going to have to use more sophisticated methods because we want to capture all of these memory and feedback effects that are actually missed in most of these treatments. Actually, I don't, yeah, sorry. So now I'm going to do something which will seem very strange to you. I'm going to solve the problem of a qubit, which is not even interacting with a bath, in what you might think of as a ridiculously complicated way. So I'm going to take, again, this Hamiltonian here, and just to notice that the angle of the field that one is talking about here, which produces this Hamiltonian, is just given in this elementary way. And I'm going to calculate, first of all, I'm going to calculate the time dependence of the propagator, which is just telling you the amplitude if you start off in one state for it to end up in another state sometime later. And then I'm going to calculate the time dependence of the density matrix. Now, of course, you can, undergraduates in their first course in quantum mechanics can solve this problem really simply. So if we want to calculate the amplitude for the spin to start off in a state which is either up or down here, so tau z is either up or down at time t prime, and then finish off in a state tau z later, then, well, we just use the Schrödinger equation for this extremely simple Hamiltonian. And so we end up with this formula here. This is exponential of minus I times the Hamiltonian times the time difference. And that's extremely easy to solve. And in fact, we find that the propagator for this particle to start up, sorry, for the qubit to start up in spin up and end up spin up a time t later is going like cos of delta 0 t. By the way, I've made epsilon 0 here equal to 0 just to make things really simple. And the amplitude for it to flip in that time is minus I times sine delta t. So it's just basically oscillating back and forth between up and down at a frequency of delta 0. Fine. But there's another way to calculate this, which is using a path integral. And you might think, well, how on earth would I do that? I now have to calculate this very strange thing, and if you're not used to path integrals, then it's not obvious at all. So the way we do it is as follows. We actually so this is e to the I over h bar times the action. Okay? So let's ask ourselves, what is the action accumulated by this system in a time dt? So that's this ds here. Well, if there's no longitudinal field, then the only contributions to the action occur when the spin flips. And in that case, there'll be an amplitude minus I times delta 0 during a time dt, but it has to flip. And in that case, we calculate the path integral by summing over all possible paths in which the qubit flips some number of times. So the amplitude for it to flip is this minus I delta 0, and I'm going to calculate the amplitude for it to start off in state up and finish in state up after a time t. Well, it has to flip an even number of times to do that. So we sum over all possible numbers of flips, and this amplitude is to the power 2n, and then we have to integrate over all possible times at which these flips can occur. So this shows you one path in which the system flips 4 times. It starts off up, finishes off up, flips 4 times in between at 4 different times, which we have to integrate over. So you think this is ridiculously complicated, but actually if I do all of these integrations, I just end up with cos delta t. It's actually very simple. This is just if I expand cos delta t, it's the real part of e to the I delta t, and if I expand the exponential, I just get this series. Likewise for the flip amplitude, but now we have to have an odd number of flips. So you think, well, this is an incredibly complicated way of deriving something really simple. Indeed it is. Sometimes it pays to do a lot of hard work at the beginning, as we'll see. If I want to do this for a general case where the system is now also in a longitudinal field, so I have some arbitrary angle, well, that's fine. I can do that too. Now the amplitudes look terrible because I'm also accumulating a phase, given here, while the system is in one or other state, because this, so in a time dt, the action is e to the I over h bar times the field on the qubit, because it now has an energy. Okay? So this gets more complicated. Now we have all these ridiculous phase contributions in each of the time integrals. You think, God, that's terrible. But actually it's not, because this is just these are just convolutions, these integrals. So all I have to do is Laplace transform, and I end up with product. And so if I Laplace transform, then, for example, I now have again, I'm summing over all possible even numbers of flips, and the Laplace transform of this exponential here is just 1 over p squared plus epsilon 0 squared. And of course, this is a simple series to sum. And then when I transform it back again, I get exactly this answer for the amplitude for it to start off in state up and end up in state up. This is cos of, this is the formula here. It contains both a cosine and a sine term, because the spin is now, the field is now tilted, where where epsilon 0 is actually the new splitting between the two levels in the presence of this total field. You see that, of course, if I have a total field like this, then the splitting of the two levels is now square root of epsilon 0 squared plus delta 0 squared. Okay? So that's the new splitting, and everything depends on that energy. And this is exactly what you get using elementary quantum mechanics when you have a field on a spin which is tilted with respect to the z-axis. If you want to think of this in a two-well analogy, where the qubit levels are just the lowest levels of a two-well system, then what we've done is we've biased the wells. So again, you say, why am I doing this? It's such a complicated way to derive such a simple answer. Well, the reason we're doing that is because of something I told you in the first lecture. It's that when we want to couple the system to a bath, we want to be able to analyze exactly the effect of the bath. And that is impossible if you start using quantum master equations, because you're throwing away important physics. You're throwing away memory effects of some kind, and as I'll discuss later, you're throwing away other things too. Whereas in principle, the formulation using the path integrals is exact. And in fact, if the bath concerned can be represented as oscillators, we can do the calculations exactly. So now what we're going to do, before I do that, just let me mention that if I want to generalize all of this to a density matrix dynamics, well, now I have to deal with two paths. I explained this also in the first lecture. Now I have the path of the, if you think about the density matrix in wave function language, you remember you have the outer product of psi and psi cross. So one of these paths refers to the evolution of the wave function, the other to its complex conjugate. But in any case, in path integral language, we deal with the propagator for the density matrix is a sum over a pair of paths with the exponent now the difference of the actions between the two paths. So if I now do exactly the same thing as I did here for a single path with all of this, then I can calculate the propagator for the density matrix in exactly the same way. Okay, so now let's go to the problem that we're interested in, which is we have a qubit coupled to some environment. And at the moment, I haven't said anything about what that environment might be. And as I described in the first lecture, what this means is that in that integral that I just showed you here, for a free qubit density matrix, I'm now going to add this weighting function here. And this weighting function has to be calculated. And as I discussed in the first lecture, we can calculate it for both a bath of oscillators and for a bath of spins. For a bath of oscillators, I'm just going to describe for you what the form of this weighting function here is. Remember, this weights the different paths, and in general, it will try and stop the two paths in the density matrix from separating too far. And this is what we call decoherence. So let me define two variables. One of them is the sum of the paths, So, in other words, I'm summing the values of this path and this path at a given time. So, for example, here it's up plus up, and if I say that the value of this is 1 and the value of this is 1, that means that the value of the sum is 2 here. But now this one flips before this one, so then the value becomes 0. And now at this time, the value is -1 plus -1, so it's -2. So you see that the value of what we might call the center of mass coordinate is basically cycling between 2, 0, and -2. Likewise, the difference is also cycling between 2, 0, and -2. Actually, we often just divide by 2 for all of these, and then we see that we have a system in which both the sum and difference variables are cycling between 1, 0, and -1. And in the calculation of the dynamics of the density matrix, it's these variables that actually interact with each other. This weighting function is an exponential of I over h bar times what we might call a reactive part and a decaying part. The reactive part is basically the effect of the environment in adjusting the phase. In engineering language, this would be called the reactive part of a resistance coming from, say, an inductor or a capacitor. And then this would be the decaying part, which would come from a resistance. But you notice that these are functions of the paths. So in the reactive part, we have interactions between the center of mass and the difference coordinate. But in this decaying part, we have only interactions between the difference coordinates. And this is what is sometimes called the decoherence functional. And for an oscillator bath, one basically writes all of these functions in terms of what's called a spectral function, which is basically just telling you the weight of the oscillators at that particular frequency multiplied by the coupling constant squared. Now you see that the decoherence is going to depend on the form of this function here as a function of the time differences. What this weighting function does is it creates, and I described this in the first lecture, is it creates interactions between these flips. Actually, for the density matrix, it creates interactions between the sum and the difference variables, but these are also things that are flipping. And if you want to think of this in statistical mechanics language, what we now have is a set of kinks, in other words, flips in these variables, which will now, in fact, interact, mediated by this function here, this weighting function. If I expand this exponential, I will, in fact, generate a large number of diagrams, which I showed you in the first lecture. But these can be thought of as interactions between these kinks. The kink can interact with itself, or it can interact with other kinks. So this is just like the problem of a set of spins on a line with interactions between them. Except, crucially, the interactions are retarded in time. So these are not static interactions. This is not the kind of spin chain problem that people are used to, where you just have static interactions with some dependence on the range, because these things have dynamic properties. So the more appropriate analogy is to imagine a set of spins on a line which are interacting through the exchange of some particle, and there's retardation effects and memory effects. So when we come to analyze the problem of an atom, a two-level atom coupled to photons, we'll find that the interactions between the kinks in this density matrix functional are actually photons. Okay? And that, of course, is a problem that we think we understand. It would be like a one-dimensional laser, in fact. If we interact with background spins, as I'll discuss, the representation of this path integral is actually quite different. We can think about, it turns out we can write the answer not in this very complicated form, but in a much simpler form, where we take the free qubit density matrix as a function of time with no bath at all, and then we perform certain averages on it. But this free qubit depends on parameters which are linked to the bath. I'll discuss that in a minute. So let me just remind you of some results that are known for what's usually called the spin boson problem. There are two big reviews in this field, which I cited in the first lecture, and the spin boson problem is covered in a well-known review article by Leggett and Company. So if I couple my qubit to photons or phonons, actually it could also be spin waves or something else like that, then the results for the time evolution of the density matrix are actually rather well known. So here I'm looking at the amplitude for my qubit to start off in an up state and finish in an up state. And I'm, again, making things simple by assuming that epsilon 0, the longitudinal field, is 0. And then we find damped oscillations. We find that, first of all, the splitting here between the two levels is actually renormalized. So this is a well-known function. It's called the Debye-Wohler, or sometimes well, there are various names that are given to it depending on which field you work in. But this basically tells you that the qubit is slowed down by its coupling to the phonons or the photons. So this is a renormalization of the splitting. Of course, in QED, it's unobservable unless you have a cavity, because you can't vary the coupling. However, it actually does. But if you vary the coupling, or if you put the thing in a cavity, you can vary this J of omega. And so this, of course, is well known. You can actually vary the effective coupling to photons in a cavity and change this renormalization of the splitting. Then you can actually observe it. Of course, you don't know the original splitting without photons. But there's also a damping here, which, of course, gives us a line width in QED. And that damping is temperature dependent. No big surprise. Okay, so this all looks very simple, and it tells us that the effects of the bath, in the case where we have photons or phonons, is actually not all that complicated. And the reason is that the spectral function for this system actually goes like omega squared. In other words, it's weak at low frequencies. It's infrared weak. We all know this. There are more photons at high energy than there are at low energies. But you see, when I Fourier transform that to find my influence functional, my decoherence functional, that means that it's short-ranged in time. It only acts over short ranges. So we have essentially local interactions. And the problem of finding the exact dynamics of the central qubit, the atom in QED, is actually made much simpler. So we have local interactions, no long-time retardation effects, and so we get this answer. And in fact, it tells you that perturbation theory is pretty good for this problem, unless the coupling is strong. Then we have to deal with lots of interactions, but still, it can be solved. However, J of omega doesn't necessarily take the simple form in QED. So, for example, condensed matter physicists study, for example, the context of the Kondo effect, the interaction of a qubit, a spin, with an electron bath. And there, J of omega is linear in omega. And things change completely. You see that this integral now becomes divergent. This renormalization no longer makes any sense. And we get what's called an infrared catastrophe. And in fact, the results are totally different. This is an extremely badly reproduced phase diagram for this system. There's a dimensionless coupling alpha. Essentially, J of omega looks like alpha times omega, the spectral function. And if we vary alpha, the behavior of the system changes completely. So when alpha is greater than 1, actually the qubit is frozen completely. It can no longer do anything. If you like, this is renormalized to 0, and literally the spin is frozen at 0 temperature. So the infrared catastrophe is so severe that the bath prevents any dynamics at all for the qubit. If I lower alpha, it'll start moving again, but completely incoherently in this regime. This is completely incoherent. Then we get to something called the Toulouse line. This is after Gérard Toulouse, who was looking at this problem a long time ago. And at this point, coherence starts to return, and we start to get actually these damped oscillations again, only in a regime where the temperature is low. The behavior is much more complicated at finite temperature. And this, by the way, is for zero bias. In other words, epsilon, the longitudinal field, is 0. If you look at the relaxation rate as a function of temperature for some given value of alpha, well, there's this delta 0 squared over some energy denominator, which is what you'd expect from second order, from Fermi's golden rule. But then we find this very strange dependence on temperature, and you notice that when alpha equals 1/2, this thing becomes flat. And after that, there is no relaxation. You can't properly define a relaxation, and as I say, it freezes here. So you see that the behavior is much more complicated when the interactions in this picture between the kinks are long range in time. In fact, what is happening is, if you like, a catastrophic memory effect. If the qubit flips, it perturbs the bath, and then those perturbations react back later in time on the qubit. And and in the case where we have this ohmic coupling, there's a long time tail in that retarded interaction, which completely freezes the dynamics. So these are known results. They've been around for quite a while now. Now let's go to a quite different problem. Imagine that my central qubit is now coupled not to oscillators, but to a bath of two-level systems, spins. As I described in the first lecture, this could be anything from defects in a solid to nuclear spins, spin impurities. In an ion trap, for example, it's now understood that what used to be called patch potentials are now actually just charge fluctuators. That is to say, they're two-level systems in the electrodes. So these are very common. So this is a problem that's of worry, which is very worrying to anyone working in the attempt to make quantum computers. Now, as I said before, we can write the dynamics of the density matrix in this very strange form where we start off with a free evolution for the density matrix, but where it depends on these parameters, and then we have these averages. Now, what I'm going to do here is I'm not going to explain this mathematically. If you want to see all the mathematical discussion and derivation, you can go to review articles. What I'm going to do is I'm going to describe physically what are the mechanisms here. So this is to give you the intuition for what's actually happening when a qubit couples to a bath of spins. So the first thing that happens is that the spins, that is the bath spins, are accumulating phases that are coming from the interaction with the central qubit. And you can think of these as Berry phases. Okay? And the most important of these contributions can be understood in the following way. Imagine that each time my qubit flips, the field on a bath spin changes. So there are two possible fields on the bath spin, depending on the orientation of the qubit. So if this is showing this in a picture, if the qubit is up, then this is supposed to be the total field on the bath spin. So you notice that there's a field on the bath spin which is not coming from the qubit, some independent static field, and there's a field coming from the qubit. When the qubit flips, that field changes and it goes to here. Now, one of the wonderful things about path integrals is that you don't have to start then thinking, oh, okay, what about the operator algebra and so forth? All you have to do is ask, what are the classical paths for the classical system? Well, a classical spin, which has a field flipping back and forth between two orientations, is simply going to try and follow the field by precessing. So imagine that we start off with the field here and my bath spin is oriented along it. Then the field flips, so the bath spin will start to precess. But then it flips back again, so it'll start, whoops. So it'll start to flip, it'll start to precess around the old field, and then the new field, and then the old field. So it keeps on trying to follow the field, but it's never pointing in the right direction, so it's always trying to precess around some field. Now, what that means is that the evolution of the bath spin in time is conditional on what the qubit is doing. If the qubit just stays there, the bath spin will just sit there. But if the qubit starts flipping back and forth, the bath spin is going to follow some complicated precessional path, which depends on the details of the time evolution of the qubit. But you see, this is just a very long-winded way in path integral language of saying that the bath spin is now entangling with the qubit because its time evolution depends on the time evolution of the qubit. Their phases now become entangled. Now, another key point about this is that there is no dissipation because the spin is only precessing, so it doesn't change its energy. Now, it turns out this is an extremely powerful decoherence mechanism. When the first experiments were done on squids by the group of Moy in Delft looking for coherence, they calculated the time, the decoherence time using Caldera-Leggett theory, which included the coupling to all the oscillator degrees of freedom in the environment. And they arrived at a time for that experiment of 12 milliseconds. But they actually found 1 nanosecond in the experiment. And the reason was a very large number of two-level systems, mostly in the junction, but also nuclear spins inside the superconductor, and so on. Now, they were expecting this, and they attributed the effect to what they called charge fluctuators, and that is, in fact, most of the two-level systems in the system. The point is that these two-level systems are not visible when you look at the dissipative properties of a squid. All you see there is the quasi-particle dissipation and dissipation in resistors connected with the squid. But you don't see dissipation from the two-level systems. So in other words, if you just used the Caldera-Leggett theory and tried to parameterize the coupling to the environment by looking at the effect of resistance, you completely miss all of this. And so that's why the decoherence was so radically affected by the two-level systems, but it had no effect on the dissipative properties. It's because all of the decoherence is coming from this mechanism, okay, which is non-dissipative. So this is a very important mechanism, and it's usually called precessional decoherence for a spin bath. There's actually another one which I won't talk about because it's far, far smaller. If you're interested in the details, they're in the supplementary notes and in the review article. Now, there's another problem that one has to deal with in a spin bath, which is if I take a qubit, which has two levels, and I couple it to a bath of spins, then of course I now end up with a very large number of levels because they're all coupled. So if I have n bath spins and one qubit, the total number of levels is 2 to the power n plus 1, which is a lot of levels. And in fact, a lot of the work in the theory of adiabatic quantum computation recently has been asking, well, what happens if I couple my adiabatic quantum computer to all of these levels? You get lots of level crossing as you vary in time, the adiabatic quantum computation. Well, the way to look at this is as follows. Think of this as a manifold of bath levels associated with each qubit level. Of course, if the number of bath spins is large, this is just going to add up and look like some enormous Gaussian with 2 to the n states. But we can actually divide these states up according to their total polarization. So these are the bath spin variables, and the total polarization along, I'm choosing the z-axis, I'm going to call m. If a bath spin flips, then m changes by 2. And so this entire bath will move from this group to another group with a different m. So we call these polarization groups. And what's crucial is that in most baths, the bath itself can't change its polarization group because the only flip processes involve pairs of spins going like this, unless you have dipolar interactions. And when we couple to the central spin, that's the only mechanism for changing the polarization group. And so it turns out that we can actually analyze that there's another decoherence mechanism associated with, which is energy dissipative, because it's changing energies for the bath. However, it's slow. So it turns out that spin baths are huge sources of decoherence, but not much energy dissipation. Oscillator baths are actually more or less the other way around. They cause much more energy dissipation than decoherence, except at high temperatures. We'll see that this is extremely important when you want to design a quantum computer. It leads to what's called a coherence window, where you can minimize both. Now, I showed you earlier the line shape that everybody loves in a typical quantum optics experiment. This is the line shape that you expect when you couple a central spin to a spin bath. Or this is one example. This is the contribution from m equals 0 transitions. In other words, no change in m. This is actually a very strong coupling to a spin bath. And you see that the line shape doesn't look like anything you've ever seen before. So there's starting now to be evidence in experiments on magnetic systems for such line shapes in microwave experiments, where you couple some spin to a set of nuclear spins, some qubit to a set of nuclear spins. This is going to become more and more important as time goes on, because as we'll see, at low temperatures, most of the decoherence in qubit systems comes from the spin bath. Okay, so that's the end of the theory. Now I'm going to discuss for you very quickly, because I see time is running out, a real system. So this is one of many examples of solid-state qubit systems that are being discussed these days. This one has been discussed in enormous detail in the literature. So it's a spin. It's actually made from a molecule containing a large number of species of atom. There's carbon, oxygen, nitrogen, bromine, hydrogen, and iron, Fe. And there's 8 of these iron ions. And the total Hamiltonian for this basically has a negative term along the z-axis and a positive term along the x-axis. And we can forget about this. And this is just the Zeeman coupling to this, which actually has a total spin of 10. So all of these iron subspins lock together and form what's called a giant spin. And I've showed in this picture here what the potential looks like on the block sphere. So when it's light in color, that means low potential for the spin. So it means it has a low energy in this direction and also this direction. Where it's dark, it's a high energy. So the spin can tunnel between these two potential wells along these paths, the red line, and also on the other side. So you see that there are 2 ways for it to get from up to down. It can either go along this path or on the other side. So what we have here is an example of an Aharonov-Bohm effect in spin space. In other words, there's going to be phase interference between these 2 paths, and I'll show you the effect of that in a second. We can actually apply a magnetic field along this axis that will lower the height of this potential hill. It'll actually raise the height of the hill on the other side. And it'll move this minimum over to here and that minimum over to there, and it'll mean that the paths change as well. Now, as was shown by Berry and Haldane, the phase interference between these 2 paths in spin space is just given by the enclosed area of the 2 paths. So it's just like ordinary 2-slit interference in real space, except that now we have a flux between the paths, which is just given by the area times the spin. You can also look at this in a more conventional way as tunneling over a barrier, but I'm not going to do that because the path integral way is much more fruitful. If I now calculate the splitting between the symmetric and antisymmetric combinations of those 2 states, up and down, this is what it looks like as a function of the field. Let's look at the one here. This is along the x-axis. This is where I applied the field along this direction. So it remains symmetric. The 2 paths are symmetric. Then we see that the splitting, this is a logarithmic scale, the splitting oscillates. And that's because we're slowly decreasing the area between the 2 paths, and every time it's a multiple of pi, we get 0. And so we see oscillations in the splitting between the 2 states. So in other words, we can control the splitting between these 2 states by this transverse field. Actually, if I vary the angle, it's different. Now, a key point here is that eventually the splitting becomes very large in the field. And that's what you would expect, because now you're dealing with a split between 2 states oriented along the field. You've gotten rid of the energy barrier. In fact, in principle, we can address this molecule by using microwaves, and that's what can be done in experiments. This is showing the states in a field along this axis. Now, what this means is that we can, at low temperatures, discuss the whole problem as a qubit, because only the 2 lowest levels are involved. Actually, it turns out that in this system, that's below 0.36 Kelvin. It becomes essentially a qubit system. of exactly the same form as we discussed before, where the longitudinal field depends on the real field applied to the system, and this transverse field is just the tunneling between the up and down states. There's a very anisotropic G factor in this system, and now I want to ask, what is the effect, what is the decoherence in this system? I'm going to tell you, but not in this lecture, that very, very extensive experiments have been done on this system by a large number of different groups. So the theory I'm going to talk about now, I will show you experiments next time in the context of qubit networks. There are 213 nuclear spins in this system. The hyperfine couplings can all be calculated very simply, and in fact they're also measurable in most cases. So we know what they are. They vary up to about 80 megahertz for the coupling to the iron 57. These are the couplings to the different protons, and I haven't shown the other species, bromine, carbon, oxygen, and so on. We can write an effective Hamiltonian for the two-level system, the qubit, coupled to these bath spins. I won't go into the details. And we can calculate the decoherence rate for this system, depending on what nuclear spins we have. Now, one of the beauties of this molecule is that people can isotopically change the nuclear spins. So they can substitute deuterium for protons, for example. That increases the hyperfine coupling by a factor of 15, it turns out, because we're dealing with the square of the moment. The iron 57 can be doped instead of iron 56. Iron 56 has no nuclear spin, and so on. So they've actually been able to, in the experiments, change all of the isotopes and vary the coupling to the spin bath over a wide range. And we can calculate the decoherence rates expected for different isotopic concentrations. This is actually, I'm going to show on the next slide what the key point. But we also have to deal with phonons in this system, and that's a problem of the kind that people are used to here. It's just like coupling to photons. So it's easy to calculate decoherence rates from phonons. And this is what you finally get. This is a function of the transverse field on the system. This is the decoherence, so this is a dimensionless decoherence rate. So if I'm at 1 here, that means critical damping. If I'm at 10 to the minus 6, that means the Q factor of my qubit is 10 to the 6th. Up here, of course, we're not interested. So what we're interested in having a very low decoherence rate. As we switch on the field, the coupling to the phonons increases because I'm increasing the splitting of the qubit. So I'm accessing higher and higher energy phonons. So it's just like in QED, if you increase the separation between the levels of an atom, you get more and more decoherence from photons. So we see that this goes up with field. But the nuclear spin decoherence rate's coming way down. And that's because we're making the qubit flip faster and faster, and the nuclear spins cannot follow, essentially. So this precessional decoherence can no longer operate. If the nuclear spins, if the qubit field is flipping back and forth really fast, the nuclear spins just go like this. Okay? This is motional narrowing, if you like. And so the nuclear spin decoherence rates come crashing down. And this is the coherence window here, where we can get 10 to the minus 5. Actually, I'll show you experiments where they tuned things a little bit differently in this, and they managed to get a decoherence rate of 10 to the minus 7. In other words, a Q factor of 10 to the 7. And in theory, it can go up to 10 to the 9 in this system. That's pretty good. So that's what I wanted to tell you. That was my real-world example, and I think I've run over time. So thank you.